Hi, it's Robin. This is another 8-Bit Book Club. Some time ago, we took a look at Programming the Commodore 64, the definitive guide, which in a lot of ways I now consider the ultimate Commodore 64 programming reference guide. The book is so big that even at a high level, I only managed to get through the first 6 chapters last time, up to Advanced Basic, and stopped at the beginning of Machine Language. And the book actually has 17 chapters in total, plus some extra appendices. So I thought I'd continue, but since the time I made that first episode, I now have the revised edition, thanks to a donation from viewer Dane. So thanks again, Dane, for that. Now, this has a spiral bound, but if I understand correctly, the book actually just has spine just like this one, but the spine was chopped off so that this book could be scanned, and then it was spiral bound after. So the advantage of that, of course, is that the book will lie flat. So actually, I'm glad for that. I know some people get upset if you modify a book at all. This is done so well and so cleanly that I'm not going to complain. I actually looked at the difference between the original and revised edition. When I first received this book, I made a video about quite a few donations I had. But basically, we figured out that the revised edition essentially had an extra introduction in it here, which just shows the things that happened in the couple years since the original book was published, such as the Commodore 128 being introduced, and so on. So just a small, basically an update in that introduction. And then at the end, some extra appendices, starting with Appendix S, some extra character and screen location tables, and then a number of extra sections about GEOS. So really, they very much did the same thing that mapping the Commodore 64 and 64C. This is the second edition, or the revised edition, and essentially it's the same book with a bunch of extra GEOS stuff in it. Likewise, same with the revised edition of Programming the Commodore 64. So all that to say, if you're looking for this book, even the original is rare enough. The revised edition's even more rare, but I wouldn't get too hung up on trying to find this one. You're not missing much. So last time we made it through to the end of chapter 6. And today we're going to start with chapter 7 and look at some of the machine language chapters. In case it's not obvious, my goal with these videos is not to read the full book to you. And while I'll try to keep my hands off not blocking the text, the goal of these videos is to make you aware of the wealth of information in these books. I'm not going to be able to read it all, and you're not going to really be able to read the whole book in this video. You should be able to easily find a PDF of it, either on archive.org or perhaps the BombJack website. That's the main point of these videos, to make you aware of the information that's available in these books, and you can decide whether it's worth it to you to either find a physical copy of the book or find the PDF and read it for yourself. Okay, so continuing on, Chapter 7, 6510 Machine Language, an introduction to 6510 ML, Machine Language Programming, description of the 6510 chip, 6510 Machine Language Techniques, monitors for the 64, monitor command dictionary, and assemblers for the 64. So if you're not aware, the 6510 is the CPU in the Commodore 64. It's essentially the same as the 6502 processor. That's in the VIC-20 and the Apple II, or the early Apple II, in the 1541 disk drive even. And the machine languages between the 6502 and 6510 are identical. The only difference really is a input-output port in location 0 and 1 of the 6510. That enables the advanced memory configurations that the Commodore 64 has over a lot of other computers of that era. And actually, there was a chapter about that. Actually, you can learn about that in this book back around page 115. We already looked at that in the previous episode. So this is an introduction to machine language programming. I totally recommend Jim Butterfield's book that I already did a video about. It's always good to learn from multiple teachers or from multiple authors. You never know what you might learn with just a different perspective. So I do recommend this as well. This is an introduction. The first example is just basically showing the equivalent of poking a single character to the screen. And so it just gives a very short example program written for Supermon, which is Jim Butterfield's machine language monitor, using the A or assemble command. And it shows that the same program could be entered in hex, which is machine code. Usually when we say machine language, we mean the opcode, the mnemonic, such as load A, store A, and BRK break. These are easier human-readable mnemonics. This is exactly the same program. The A9 hex corresponds to the load A. The 0 corresponds to the 0 that's loaded into the accumulator. 8D is for store A. 0004 is a 16-bit address, two 8-bit values combined to this 16-bit value, and it's done in low byte, high byte format. And in these examples, like in Jim Butterfield's book, programs end with a break, but if you want this program to be runnable from BASIC with a sys, or not runnable, sysable, then you should change that to an RTS, return from subroutine, which instead of being a 0 byte is a 60. So I prefer Jim Butterfield's approach to this, but I think this is good too. This is worth reading. Second example, poking a character with its color. So this is a very similar program, but it's also storing black in the color RAM. And it shows the program again in both assembly that the Supermon assembler can handle and in direct hex. Example 3, using an index, using the X register as an index. So you can, instead of just addressing a single byte in memory, you can reach a 256 byte range. So you see how the programs are getting just a little bit more involved each step. Here's doing loops, and he's comparing it to a for next loop in BASIC. Well, there is the for next loop in BASIC. Personally, I think this is a very good way of learning assembly language. In a couple of my previous videos, I've shown BASIC and then machine language equivalents. And personally, I find it very useful. Example 5, comparisons and subroutines in machine language. Now we're starting to get into comparing and branching for loops. Okay, so that's the end of the examples. Jim Butterfield's book is more thorough, but this is a good start. Now there's a section describing the 6510 chip. Talks about the status register, the interrupt vectors, the opcodes, addressing modes, and goes through each one, single byte instructions, 2-byte instructions. Actually, I like these different ways of grouping the instructions together. Single byte instructions are ones where the addressing is implied, like ASL, arithmetic shift left. It only operates on the accumulator and doesn't require any parameters. But some monitors require you to type ASL-A rather than just ASL. I've seen some assemblers that require you to differentiate it from ASL on like a memory address or a label. 2-byte instructions, such as 0 page indexed by X, 0 page indexed by Y, indexed indirect, and indirect indexed. And then 3-byte instructions, absolute indexed by X, absolute indexed by Y, absolute indirect. If you have no familiarity with this, really I recommend you get Jim Butterfield's book or just watch my video. I'll put a link to the Jim Butterfield video, and that book is highly recommended by me. Okay, now a section on the status register. These are all the individual bits that allow the 6510 to make decisions in your code. For example, if you compare two values and they're equal, then the 0 bit will be set. That's because to do a compare, the CPU actually subtracts the two values, and if the remainder is 0, then of course they are equal. Some of these flags seem confusing, but that's why reading it from multiple authors is definitely a good idea. The 0 flag, depending on context, sometimes you want it to be called the 0 flag, other times you want it to be called like the equals flag. So it just depends on the context of what you're checking. The negative flag, yeah, so it just goes through them one by one. Actually calls bit 5 the 1 flag. I've actually never heard it called that before, besides this book, but it's unused since it's always set to 1, is referred to in this book as the 1 flag. The B or break flag, decimal, the interrupt disable flag, the 0 flag, and the carry flag, which is very useful for all kinds of mathematical operations and comparisons. The program counter is the 16-bit register that points to the current instruction being executed. Normally it just increments through memory, executing the program there, but when you do something like a jump or a branch, it changes its value to the new location. The various interrupt, the NMI, reset, and interrupt IRQ vectors. 6510 instructions and opcodes. Adding, subtracting. So here they've all been grouped together. There's 56 different mnemonics, but many of them have multiple addressing modes, as many as 8, for a total of 151 valid opcodes. That is 56 different mnemonics, such as load A, but there's different addressing modes, different ways of loading things into the accumulator. So that's why there's 151 valid opcodes. And then he's grouped them: add and subtract, branches, break, comparisons, data transfers, decrements, increments, flag clear or set, jumps, logical operations like AND or exclusive OR, the no-op, returning from a subroutine or returning from an interrupt, rotate and shift, stack operations such as pushing or pulling off of the stack, transferring between the registers. Timing, well, how the C64's chip runs at about 1 million cycles per second, and different instructions take differing number of clock cycles. So here's a different timing chart that I've never seen before. Just a different way of looking at how many cycles do the different addressing modes take, and then exceptions. That's a different way of looking at it. 6510 machine language techniques. So here's little examples of how to do operations that are bigger than just what a single opcode can do. Such as if you want to increment 2 bytes together, here you increment the low byte, you check if it is not equal to 0, and then you increment the high byte if it is. So that's a good way of doing it. Decrementing isn't quite as simple. It takes 1 extra instruction. Adding 2 byte pairs. 6510 is only 8-bit. If you want to deal with larger values than 8-bit, you have to chain commands. And so there's an example. Oh, here's a multiply using rotate. That's interesting. Shift and rotate, logical instructions. 2's complement arithmetic. So if you've wondered about how negative values are represented in assembly, here's a write-up. Using decimal mode. I did an episode about that before. Debugging machine language programs. Listed here are many errors common in 6510 machine language programming. Careless errors, addressing mode errors. That's pretty common using the wrong addressing mode. Calculation errors where you're forgetting things like clear carry or set carry. Status flag errors. Stack errors. Errors in which RAM is overwritten. Monitors for the Commodore 64. These are machine language monitors, and they're called that because they allow you to monitor memory monitor the CPU. Just, we're not talking about CRTs here. We're not talking about displays, screens. So you can have a monitor written in BASIC, just essentially they're just peeks and pokes. Actually, this is kind of interesting. He's calling them differentiating between basic monitors and machine language monitors. I would still call a machine language monitor written in BASIC would still be a machine language monitor. So it's almost like this is machine language monitors. That is, the monitor allows you to change and monitor, look at machine language, whether it's written in BASIC or not. But these are fast and generally better than BASIC. Okay. And they'll concentrate on Supermon, a public domain program which is the work of several people, including Jim Butterfield. I've noticed a slight tendency by Rayto West to downplay Jim Butterfield, to mention him as seldom as possible. I don't know if there's a little bit of something between them. It is true. Jim himself acknowledged that Supermon was built upon the work of some other people. Although I think by the end, Jim had pulled it all together and maintained it for years and adapted it to each new computer that came along. Those early contributions were still important, but it's kind of funny to be by 1985, or in this edition, 1987, still be saying, it was several people, and Jim Butterfield did a bit. I don't know. Anyway, a bunch of instructions about using Supermon. Supermon's still great, but nowadays I recommend getting a utility cartridge like the Super Snapshot, Action Replay, or if you like something else, that's fine. They're so handy that they're built right into the cartridge. You just hit the button on the cartridge and you're into the machine language monitor, and they're a lot more transparent to the program. You can freeze many games, jump into the monitor, check something out, make a change, and then resume the program after. Generally, that's a lot better than Supermon. And going through the instructions, Micromon, here's another one. Micromon is very similar to CBMmon. That's a smaller version. A lot of these monitors are kind of interwoven, or the one built into the original PET, for example, was then extended by Jim Butterfield. And then by the time we got to the 64, Supermon was standalone. And then the Commodore 128 has a built-in monitor as well. And it has a lot of similarities with Supermon. So there's kind of a real sharing there going on. I don't think anybody was stealing anything. Back then, that sort of thing people were a lot more free about. Okay, and so there's some instructions on how to use a monitor, what to do if your machine language crashes, monitor command dictionary. Okay, this is cool. So A is assembling. So Supermon does have an assembler, but it is a non-symbolic assembler. It recognizes all the mnemonic opcodes like load A and store A, but it does not allow you to attach labels to memory addresses. So if you want to branch ahead, you can't say branch to loop or jump to read joystick. You can only say jump to and give it a hex address. And that's a real limitation when you're developing more complicated programs, because you don't necessarily know where in memory that jump or branch is yet, because you haven't written that, or you want to add or subtract some code. Then some of those addresses where those instructions are in memory may change. So that's why a symbolic assembler like TurboMacro Pro, or all the many cross assemblers available now for modern PCs, if you're writing a bigger program, you definitely want a real symbolic assembler. But for writing little examples like this, the one that's built into Supermon or the Super Snapshot monitor is fine. Jim Butterfield actually recommended learning this way first because it gives you an appreciation for how the instructions and the data are all in shared RAM. And that way you understand that when you go to the assembler, I think you appreciate it more and you can make better decisions based on the understanding that you get here. Comparing memory. C, and you can type a range, and it'll tell you if any bytes are different. Disassembling, this will turn the contents of memory back into instructions like increment Y, branch if equal, JSR. But again, it doesn't do symbols. It just does a raw disassembly. And sometimes it's not perfect because it doesn't know the difference between data or opcodes in certain contexts. So sometimes you'll see gibberish. If you try to disassemble, you might get gibberish. And that's probably because it is interpreting some data as opcodes. F for fill memory. G to go, that's to execute. H for hunting, if you want to find a string like the string basic or just particular hex bytes. Interpret memory, this is nice, it shows the ASCII equivalent, and that's good for hunting for strings. Loading from cassette or disk. Memory display, a hex dump. Ooh, number adjuster. Okay, I've never used that before, but okay, so Micromon 64 uses that. When you change some address, you might move a block of machine language with T for transfer, but then absolute addresses will no longer be correct. So I guess that's what this fixes here. It's interesting. I've never seen that before. Micromon 64 instead of Supermon. Printer disassembly. R for the register display, and that shows, the various registers and the flags. Saving machine language. Transferring, and transfer if you just actually want to move block of memory. Verify, if you want to verify that your save was good. And X for exit. So many of these commands are the same across various monitors, like Super Snapshot Monitor uses many of these, like R and save and T for transfer, but it doesn't have this number adjuster, printer, verify. So it'll vary from monitor to monitor. And then here's a section about an assembler. And well, I guess I already explained this about how you can use these equates and labels instead of just hard code addresses like screen equals 0400 instead of typing 0400 every time. And the advantage isn't necessarily saving typing up front, but if you want to change something, then that's very valuable. So the job of the assembler is to convert the source code into object code, the actual numbers which make up machine language instructions. Note that the object code is a sequence of bytes identical to that produced by a simple disassembler. And it's talking about how assemblers will allow you to set star equal to, say, 2000, and then you can change that. It will then assemble the code to location 2000 or 2000 hex, as I like to say, and you can simply change that to 3000, assemble it in a new location. An overview of the assembly process. Assembler features. So it just talks about the different features of what a full symbolic assembler will allow versus the simple assembler that's built into something like Supermon. Labels, symbols, the opcodes, of course, the operands, comments, pseudo-opcodes, also known as directives. Now that varies from assembler to assembler. That's why you need a manual when you're using an assembler specific to that assembler. Typical pseudo-ops, star equals, and some use .org instead, like Merlin, which is the first assembler I ever used org instead of star. So yeah, that sets where the assembly will happen. The equal sign, sometimes EQU for Merlin. The byte opcode, or BYT, or some use DC.B for storing just raw bytes or string, and so on. Just these are ways, these don't actually generate machine language, but they do influence the assembly and sometimes insert bytes in when you want like data. Conditional assembly or macros, these are extras where you can do conditional assembly. This isn't code, like if you've got if type 1, so essentially you can set it so that the same code will assemble to different locations based on how these labels evaluate. And I've done that before, like I've worked on games, pretty simple games, that will compile either for PET or Commodore 64, but the screen memory is in a different location. There's some other changes, such as how the keyboard is read or how the waiting for vertical blank. So you can use the same source code for multiple platforms if you use conditional assembly properly. And here's a brief look at the different types of assemblers available, those written in BASIC. Assemblers with basic editing. There were some where you type your assembly language into the basic editor, but of course you can't just type run. It won't run the machine language, but the machine language or the assembly language is in the basic program. The assembler is written to interpret that basic code and turn into actual machine language. So I know some people who use those a lot. One example is Richard Mansfield's LADS assembler, which was published in the second book of machine language from Compute Books. So that was quite popular for a while. Well, I think there was one called Buddy that used that as well. And here's another one about Commodore's ASM 6440 program package. Well, that sounds really tedious to use. Don't recommend that. Anyway, I just recommend Turbo Macro Pro just because it's so easy. It's just, it has some limitations, but just that the quick turnaround, having the integrated editor and assembler, and the super fast turnaround to assemble, run, and then get back into the editing just means everything to me. Okay, Chapter 8, Machine Language Methods Specific to the 64. Kernel routines, basic ROM routines, using RAM under ROM, modifying basic vectors and interrupts. This chapter is a reference to the ROM of the 64 and a guide to using the vectors that point to that ROM effectively. You can include your own machine language routines that will wedge into the normal operations of the computer if you like, and this chapter will show you how. Other chapters that include specific machine language material are Chapter 6, keyboard, screen, etc., Chapter 12 about graphics, Chapters 13 through 17 about sound, tape, disks, and peripherals. Kernel routines. The kernel is the essential core of machine language routines that the 64 uses during normal operation. It has a jump table pointing to the routines. While the specific addresses of the routines may differ from one computer to the next, like in the VIC and 64, the addresses of the jump table are supposed to remain constant between machines. In theory, this will allow programs to work on several ROM versions of the same machine and even on different Commodore computer models. In practice, consistency among different models is achievable only to a small extent because so many hardware and software differences exist between machines. Still, it does serve a useful purpose. So David Murray's Commander X16 computer is going to have a compatible kernel, even though the computer itself has many new features and really isn't all that compatible with other Commodore computers. It is going to have a kernel. So because of that, all those basic things like loading, saving, printing a character to the screen, and so on will work on that machine. So I'm pretty excited about that. I think that's cool. Okay, so it gives a list of the different kernel routine input-output errors. Well, that's kind of cool. Type that line in. And here's a detailed look at the kernel jump table, and it gives the address for each one, the name, and a description of what that kernel routine does. So there's a number here that reset your Commodore, initializing the screen, initializing input-output devices. Sometimes these are handy if you have written a program that really messes around with the Commodore, but then you need to restore it to normal use after, like my Frogs and Flies game. I use some of these to reset the C64 when you want to quit the game and return to Lodestar Disk Magazine. So that's what those are handy for. Yeah, we won't get into all of them, but reading the keyboard, of course, is very useful. If you want to program the disk drive in machine language, then these routines are a must. Classic, chur out. FFD2, that's for printing a character. Oh yeah, here's the load from machine language. And it explains that you need to set it up correctly first. Same with save. I'd like to point out that the routine that tests the run/stop key is just called stop. I keep thinking about trying to make a video proving that the run stop key really is just called the stop key. This is the only respectable book that really likes insisting on calling it run/stop. I'm okay with calling it run/stop. I won't get into that today. Okay, and examples of using the kernel. Using plot, using get-in to fetch keyboard characters, using load and save, using scan key, using stop. So stop is called after each basic statement is executed in normal run, which is why stop works with basic. Basic ROM routines. Basic obviously has an enormous number of built-in routines, many of them having a recognizably basic feel about them. This section will show you how run can be performed from machine language and will give you an easy way to input data from the screen. Oh yeah, this is great. If you've ever had a reason that you've wanted to run basic from machine language, and I have, I puzzled over that and I could not, like using mapping the C64, I could not get that working reliably. And here is the magic incantation that would allow you to run basic code from machine language. So that's super cool. Page 250. Receiving lines from the keyboard, processing basic variables, calculations. Boy, this is really cool too. If you've ever wanted to use the math routines in BASIC from machine language, then here is a summary of how to do it. Now, while the basic routines are a little bit slow, a lot of the slowness comes from all the overhead involved in the interpretation of the basic code, like the parsing and so on. The actual routines aren't super fast, but they're pretty fast, especially for general purpose math routines. Now, if you're doing something in machine language for like a game or a demo, you're probably going to want to write your own custom table-driven routines specific to that purpose. But if you want general purpose math routines, the ones built into BASIC are pretty good. And here they are accessible as well. User function, hex to decimal conversion, random numbers, 1 or 2 byte random numbers. Lots of examples of how to use the ROMs built into BASIC from machine language. Series calculation, integer to floating point conversion powers of 2 using RAM under ROM. The Commodore 64 has 64K of RAM, but some of it is under ROM while you're in BASIC. But you can get at that RAM, so here's some discussion of that. Making modifications to RAM BASIC. So this is if you copy C64 basic ROMs into RAM, they can then be modified, like changing just ready dot to ready exclamation mark. That's cute, but it's a good, it's a fun example of what could be done. Upgrading ROMs, well, I did that whole episode. Kernel 2, Kernel 3. New languages. Putting BASIC 4 on the Commodore 64. I don't know if I ever read this part before. It's conceivable that a language like Apple BASIC might be transferable to the 64, but even if this were done, there'd be difficulties over disk drive and other hardware incompatibility. Has anybody ever made Apple BASIC run on the C64? Run, stop, restore calls the IO and net routine, which unless changed, sets location 1 to 55. Oh, okay, this is about preventing RAM BASIC from getting set back to ROM after stop restore. That's cool. Reset and RAM BASIC. So this whole section is about copying BASIC into ROM and modifying it. Programming RAM under basic ROM, modifying BASIC. Oh yeah, these are the vectors and wedge methods. So these are different ways of modifying BASIC to have new behaviors, not modifying the ROM, but instead intercepting at various vector or wedge points. And C64 BASIC was very deliberately built to be expandable. I know it gets a lot of criticism for how bad or simple it is, but they really did include a lot of hooks so that it could be improved and customized. And that's exactly what Super Snapshot, Fast Load, and other cartridges, Simon's Basic, Expander 64, there's a whole host of cartridges that all, in their own way, improve on the 64, and that was made easy by the design of the 64. So it's not all bad. So a wedge demonstration. So this book has all kinds of nice little type-in programs like this, if you want to experiment. Vectors. For example, when an error happens in BASIC, a routine at location 300 hex is called, but you can just change that to point to a different routine to handle different errors. You don't necessarily just have to print errors with that. It just prints the error and then says ready, but you could actually extend it. The main basic loop vector to tokenize keywords routine. This vector could be diverted so new keywords could be recognized and converted into tokens. Vector to untokenize keywords. So this is how BASIC can be extended with these vectors. This is the evaluate routine. Oh yeah, this is the hex one that I did an episode about. So you can poke D020, for example. Okay, more kernel vectors. So you can intercept open, close, load, and save. And this is part of how fast loaders work. They intercept the load and save commands and execute their own code instead. That runs a lot faster. Interrupt vectors. And we've dealt with that like in that music playback. I did an episode about music playback, and we intercepted these vectors to make the music playback while BASIC was running. Oh yeah, that's what he's got here. Interrupt-driven background programs. Gives a little example of them. Produces normally impossible stripes. Oh, sometime I should type that in and try that. Okay, give some instructions on it here. Okay, I think that's all we're going to get through today. 2 chapters, 7 and 8. Next time is mixing BASIC with machine language. So again, I encourage you to grab this book. Fantastic. Read the PDF and see what you can learn. All right. Thanks to my patrons for their support. Thank you for watching. We'll talk to you next time.